Hey, I guess you knew this was going to happen. How do you get the vertex form? Did you think that this was one of your favourite forms? Because, remember now, this is the X translation and this is the Y translation. So in this form, we know that the vertex is going to be not at 0, 0, like this is a little dude Y equals X squared. It's now going to be across H in the X, okay, and down K in the Y. Here K would be negative, so your new vertex is HK. So for this one, if you read the scale here, it's gone across 6, so it'd be Y equals X take 6 all squared and take 4. Okay, get the idea of it. Goes opposite to that one. The X translation is 6, and the same as this one down to -4. So this is a very powerful form. A lot of people like this because it nails the vertex perfectly. Okay, so let's have a look at creating that form from the general form or from the expanded form. Okay, this is what we want to do now. This is called the general form or the expanded form, and we want to get it in the vertex form. Why? Well, so we can find the vertex, mate. Okay, what's it called? It's called completing the square. And we're going to use it to find the vertex. We're also going to use it for finding where a function cuts the x-axis when the function isn't factorisable. So, we want to complete the square. We want to make this general form into a square plus another number, an adjusting number. Okay, because this is the X translation and this is the Y translation. So that is the new vertex. The old vertex is 0, 0. It will move to HK. Got it? You might have to go back and revise that again. Alright, let's have a look at how you do that. And to look at that, what I've suggested we do is to look at the structure of a perfect square up here. What does it comprise? Well, it's a square of the first term, twice the product of the terms, and square of the last term. Let's just check that out. Do you believe that using FOIL? Okay, so here's FOIL. A by A squared, A by B, AB, plus B by A, plus B by B is B squared. So it's A squared. Now these two are the same. Remember, multiplication is commutative. Doesn't matter which order you do the multiplication in, come to the same answer. So it's 2AB plus B squared. Now we usually, for a perfect square, remember, two brackets the same, you're squaring it, we would normally go straight to here. Okay, that's what's expected at this level now, year 11. So, how do you remember it? Well, I like this word form. It's a generic formula, isn't it? Just doesn't work for A and B. You could make it work for P plus Q all squared, and so on. So, how do you use it? Think of it as square of the first term, twice the product of the terms, square of the last term. Let's have a look at this one here that we mentioned above, x squared plus 2x take 3. Well, that's a square. That's not. So what should that be? That's what we're after now. We're going to play there and see if we can make that the correct number to be a square. So what's our clue? Here's the first term squared. This is supposed to be twice the product of the terms. So what was the term? Well, one was x. The other term down the end of the bracket in the square, we don't know. Second term squared. So this is 2, so half of that is 1. And so the other number down the end must have been a 1 as well to give us 2x. So the square on the end is 1 squared. That's what we should have. Okay, so it should be x plus 1 squared, y, because that gives x squared, gives the correct 2x term, and then you've got plus 1. But you've got -3 here. So if you add 1 squared, then you need to take that 1 squared off, and you've still got -3. So effectively it's -4. Bit hurried? Have you seen this before? Should have seen it in previous study. I'm going to go through it again though. If you expand this, you get x squared plus 2x plus 1, take 4 is neg 3. So you actually have to adjust the numbers on the end so that they still come to neg 3. But you've got your wish number here, the number you wish for to make a perfect square. Okay, might be a bit quick if you haven't studied this in detail before, so let's pull it apart more slowly now. Come down here, and steps to complete the square. Let's do them. First of all, let's write this down again, and we're going to halve the coefficient of x. So half of the coefficient of x is the number in front, half of that is 1. Square it is 1 squared. And we're going to add that on. That's our wish number. Okay, so all of this should now give us a square under the perfect square expansion rule. Okay, add it on to the expression, and so you've got that, and you've still got neg 3. Now we've got to subtract 1 squared. Why? Well, that was our wish number to make a perfect square in here. But the number that we have to end up with at the end, we can't change the value of the expression, is neg 3. So we have to balance it by taking it off down there. So all of this expression still has to come to this line. Why did we do this? Why are we playing around with 1 squared, take 1 squared? Well, hang on. Because that generates the perfect square formula, pattern. A squared plus 2ab plus b squared. And so down the end we really need neg 4. Now, this is a balancing number, if you like, the balancing number, what I'm talking down here about subtracting it to find to keep the balance. So overall, this is to adjust the balance so that we can have a square, and that's going to give us this square in here. But overall, the numbers, here they are, all the numbers must still only come to neg 3. Okay, so it's playing around with the way we write the expression to deliberately generate this perfect square bracket. Restate the expression in square form plus a constant, and that's what I've done at the end here. So that's your final constant, not neg 3, because we needed a 1 in this spot here to create that particular form. So we are creating the perfect square form. That's what we're doing, because, why? It's so valuable in us being able to work out the vertex. So we are going to replace this with this form. But they must be equal. When you expand one, you must get the other. Okay, well, when you expand the square form, you must get the general form that you're given. All right, hopefully you've seen that before. We need to practice it now. So please note down these steps, go through them carefully, and see how the mathematics behind it. Okay, let's go down now and have a look at an example. These screen clippings are from Hayes and Harris, Year 11 textbook called Functions and their Graphs, I think. Anyway, it's the function textbook. Okay, so here we are. Here's our function, and we want to write in this form. Why? Well, because we can get the vertex easily. Okay, so here's the form. What do? Halve the number in front of x, that's 2. Square it and add it on. Write down what was already there, then balance it out by taking that number off. Why did you do it? Because you wanted this special wish number in here. This is your wish list, so that it comes to, you generate the perfect square form. And now 3 take 4 is neg 1. So that's an adjusting number, if you like. Adjusts the expression back to the original. When you have your square that you want in front. Okay, that's the way of thinking about it. Okay, and then the value is of this form. What is the valuable result? Because we can say this is the x translation is neg 2. Remember, it's the opposite sign to this constant there, and a y translation of neg 1. And so we can say the vertex is at -2, -1, because the original vertex, oh hang on, we won't draw it there, over here, original vertex y equals x squared is at 0, 0. And we've said we're moving everything -2, -1. So when you move the vertex -2, -1, it goes down there and you have your new vertex. So that's the idea of it. In earlier study, hopefully the teachers showed you why this x take h squared and k up here, why that is the x translation and the y translation. We're not going to go into it here. That was covered in a Year 10 presentation. This is just a revision. All right, let's go on and practice these skills now. So I've got some problems here for you. Exercise 1B. I would suggest you do all parts here to hone up your skills. All parts. Okay, some of the more difficult ones are in the bottom line here, because you can't easily, these are not divisible by 2, these coefficients of x. So you're going to have to work with a fraction. Halve the number in front of x, square it and add it on. So you're going to have to be happy with that. Okay, I want you to try all of them, and pause the presentation now, do one, and then scroll down, scroll forward, and have a look at the answers. I'm going to show you the answers now. Here they are. Okay. Now these answers, I think the answers are okay, but sometimes the graphs don't match up. Those are okay. This is correct for B, but it's the wrong graph. The B graph is down here. That really belongs with B, and this graph here really belongs with F down here. So just be careful. They messed that up a bit, I think. I think this one is okay. No, it's not, is it? So the graphs are messed up. Where's this one here? Vertex 2, -4 belongs to this function here. So just be careful that we have in the book here mixed up graphs and functions. But just check your function. I think the functions are all okay. Let's just go back and have a peek at that. Yeah, I think here, part A, what is part A? X take 1 squared, yeah. It looks like the functions are okay. Okay, so these functions are all right for A, B, C, D, E and F, but the graphs they've matched them with are incorrect. So just check that. Okay, let's go down and look at the really most challenging one, and that is where you have a number in front of x squared. Okay, and we need to put that number out the bracket, out the front of the bracket first. Okay, this means it's going to be a steeper version of x squared, doesn't it? Remember when you put have the transformation of a dilation or a stretch in the y direction with a number there, then what this means is it changes the steepness. The steepness is affected because it's a stretch or a dilation in the x direction. All the values after squaring have been multiplied by a. Okay, let's do it. First thing is to divide through, take out a factor of 3, divide through by 3. You could be a bit challenging here as to whether that's a factor. To say divide through by 3. Factor is not, 3 is not a factor actually of 4 here. So you take out 3, divide through by it, then you say, so what do I multiply 3 by? Get 3x squared. What do I multiply 3 by to get -4x? It's -4 over 3, dividing through by 3 in other words, and just checking the expansion would give you that back again. So this is going to get messy, because now what you want to do is to halve the number in front of x. So that's 2/3, isn't it? 4/3 divided by 2 is 2/3, keeping the negative there. So you're going to add 2/3, bring the third down, then subtract 2/3, all squared, sorry. Halve the number in front of x, square it and add it on. Okay, so that will give you x take 2/3 squared. Here's your adjusting number. It's a fraction now. So the biggest problem here, because you've divided through by the 3, is you've got some fractions, and halving them is challenging. Adding them up can be challenging. What's the way to do it? 4/9 plus 1/3, change 1/3 to 9ths. So if I multiply bottom line by 3 to get 9, multiply top line by 3 as well, so you get -9th. So it is a steep dude, a steeper dude because of this, and the vertex is 2/3, -1/3. So this one doesn't actually look much steeper than x squared, so they play around with the scale here, but this should have, this is steeper because of the 3 out the front, and we want this, the vertex is 2/3 and -1/3. The y-intercept they put in, how do you get the y-intercept? Well, you've always put x is equal to 0 in the function. So up here, remember the big value of this type of function. The one thing that it is very good for is when you substitute 0 in there and 0 in there, those terms go out, and the y-intercept is always the number down the end. So that helps you locate it on the graph down there. All right, do you want to try some of these harder ones? Let's go down and have a look at them, and you might try all of these and see what you think. Convert it, state the coordinates, vertex, find the y-intercept. Remember, the y-intercept is always going to be the number down the end here. And look at this dude over here. A is always the constant to be divided through or to be taken out as a common factor. So divide through, in the first instance, by the coefficient of x squared, the number in front of x squared. All right. Okay, now this is a little different, this question down here. It's easier, as what it's saying is, graph this function, right, find the vertex. So if you graph that on the calculator, then on the Casio go shift F5 for G-solve, and then find the vertex, choose either max or min, whether it's concave or convex, concave up, concave down. Then when you've got this, of course, this max or min is a vertex. So once you've got those numbers, you can use them in the form y equals x take x value of the vertex squared plus y value of the vertex. Okay, so you're going backwards. Instead of using this form to generate the graph, you're going to go backwards, take the graph, get from technology the max or min, get the vertex, and then reconstruct your formula. Okay, so just think about that one, going backwards there. All right, have a go. I'm going to show you the answers down below here. Okay, so there's question 2, A, B, C. And then D, E, F. Go check those. And then I'll show you question 3. So remember, you're finding this formula by, first of all, get the vertex and then put that vertex x value in here, x value squared plus y value, going backwards there. Okay, this is almost covering all of the previous work you should have done in quadratic functions up to year 11. And so what we're going to do now is probably look at some x-intercepts and some variations and go on and develop the quadratic theory, because the quadratic is the simplest of polynomials. It's a gateway to the whole polynomial field, and that's important in mathematics. So good luck and keep working hard, and I'll catch you in another presentation. Cheers for now.